Next term, significance of hyperconjugation. So first coming to directive influence of alkyl group. So just now I explained that hyperconjugation in toluene. Okay. So there, due to hyperconjugation of the toluene molecule, electron density is more at ortho and para position. Okay. So here this is toluene. Okay. So displacement of sigma electrons takes place here, and alkyl group gets attached to sp2 hybrid carbon. So this is the sigma bond. Okay, sigma electron transfers towards the sp2 hybrid carbon, and the next immediately pi electrons transfers towards ortho position. That's why more electron density is there at ortho position. Okay, then it appears in different resonating structures. Okay, next, due to the transfer of electrons, pi electrons here, electron density gets increases at para position and ortho position. Okay. So more electron density that is present at ortho position and para position. Okay. And simultaneously hyperconjugation, no bond resonance is observed regarding the alkyl group also. Okay. Due to the transfer of sigma electrons there. Okay. Then here, more electron density is present at ortho and para position. That's why electrophilic substitution reactions, so they takes place at ortho and para position. Okay. So alkyl group increases electrophilic substitution reactions towards ortho and para position. Okay. So this is directive influence of alkyl group in aromatic compounds. Okay. So electrophilic substitution reactions takes place at ortho and para position. Okay, due to hyperconjugation in aromatic compounds. Next, coming to another significance, shortening of carbon-carbon single bond adjacent to multiple bond. Shortening of carbon-carbon single bond adjacent to multiple bond. So this is also just now I explained in propene molecule. Okay. So in propene molecule also we observe transfer of displacement of sigma electrons towards the sp2 hybrid carbon. Okay. So in propene molecule, single bond that partially gets converts into double bond. Okay. So partial double bond nature that is observed in propene. Okay. So in all its resonating structures. So due to the displacement of sigma electron, this is single bond. Okay. And single bond indicates a pair of electrons which are sigma electrons. So sigma electron displaces towards this single bond which gets attached to the sp2 hybrid carbon. So here single bond becomes partial double bond. Okay. So due to this, length between second carbon and third carbon gets decreases. Okay. So we will get resonating structure like this. Okay. So this is resonating structure. So single bond gets converts into double bond there. Okay. So that's why its length becomes decreased. So length of the carbon-carbon single bond that gets decreased due to the formation of double bond here. Okay. And same thing we can observe in nitriles also. For example, acetonitrile is there. In acetonitrile also we observe the hyperconjugation. So CS3CN, acetonitrile, okay, where carbon linked in between carbon and nitrogen triple bond is there. And here we observe displacement of sigma electron. So single bond which is linked with unsaturated carbon, here it also converts into double bond. Okay. So due to this, length decreases. Okay. So hyperconjugation, so that involves in the shortening of carbon-carbon single bond adjacent to multiple bond. Okay. Next, coming to relative stability of alkenes. So coming to relative stability of alkenes, it is related with heat of hydrogenation. Heat of hydrogenation of alkenes. So stability of alkenes, that inversely proportional to heat of hydrogenation. Okay? Why? Because heat of hydrogenation, the having more that shows greater influence over the compounds which having more number of alkyl groups in it. For example, we take alkene. Alkenes having double bond carbon atoms. So, double bonded carbons which linked with more number of alkyl groups. Okay? They shows the greater stability and less heat of hydrogenation. Okay? So, here relative stability of alkene, that is inversely proportional to heat of hydrogenation. Stability of alkene inversely proportional to heat of hydrogenation. Heat of hydrogenation. For example, so relative stability of alkenes. So that is inversely proportional to heat of hydrogenation. Okay. So here, if you see these three alkene compounds. So in the first compound, this is 2,3 dimethyl butadiene. 2,3 dimethyl butadiene. Okay. So here double bonded carbon atoms linked with more number of alkyl groups. Whereas in propene, only one alkyl group gets linked with a double bonded carbon atom. Then in ethene, so no alkyl group is there. So for this compound 2,3 dimethyl butadiene, heat of hydrogenation is minus 26.6 kilocalories per mole. For propane it is minus 30.1 kilocalories per mole and ethene it is minus 32.8 kilocalories per mole. So if a compound having more number of alkyl groups, it is more stable and with a lesser hydrogenation value, heat of hydrogenation value. Okay. So here it having more number of alkyl groups. That's why it is more stable in nature and it is more stable than propane. Propane is more stable than ethene or ethylene. Okay. So as stability gets decreases, heat of hydrogenation gradually increases. So, inverse proportionality to stability and heat of hydrogenation. Then stability of carbocation and free radical. I have already explained this concept. Stability of carbocation. Greater the number of alkyl groups on the positively charged carbon, greater is the hyperconjugation. Okay. Same thing is applicable for free radicals also. Okay. So for both we can give the order, hyperconjugation order. Tertiary carbocations are free radicals. Tertiary is greater than secondary, secondary is greater than primary, primary is greater than methyl. Carbocation or free radical also. Okay. So same trend. Okay.